Rules and general concepts. Now we'll talk about some of the most important rules in this standard. Dimensioning and tolerancing shall be complete, so there is full understanding of the characteristics of each feature. 90-degree angle applies where the center lines and lines depicting features are shown on a drawing at right angles and no angle is specified. Unless otherwise specified, all dimensions are applicable at 20 degrees Celsius, 68 degrees Fahrenheit. All dimensions and tolerances apply in a free state condition. This principle does not apply to non-rigid parts. Dimensions and tolerances apply only at the drawing level where they are specified. Let's see them with more detail. Each necessary dimension of an end product shall be shown. Here we can see that we are missing some dimensions to define this part. It is very basic, but it's actually helpful to know that this is stipulated in the standard rules, so you can always demand the full definition of the part in a drawing. Here are the dimensions that were missing of 10 and 8. Dimensioning and tolerancing shall clearly define engineering intent. No more dimensions than those necessary for complete definition shall be given. Here we have the opposite case. Now we see repeated dimensions in the views, which can create conflicts. For example, we can see that we have specified individual lengths, but by placing also the total length dimension, we overdefine the drawing. Since it is possible to meet the individual dimension tolerances and do not comply with the total length of 27 within tolerance. Also, notice that some dimensions such as 8 and 10 are in both views, causing confusion. That's why only the necessary dimensions should be placed. We see here the same part drawing, but now to avoid overdimensioning, we've set the repeated dimensions as reference by placing a parenthesis on them. Even though putting too many dimensions causes confusion, and sometimes reference dimensions are taken as official. Therefore, the use of reference dimensions should be minimized. Each and every one of the dimensions in a drawing shall have a tolerance specified. It is impossible to make perfect parts. It should be always specified whether a dimension is critical or not, if it's allowed much or little variation. The exception to this rule is in commercial stock sizes. For example, if a half-inch screw is specified, tolerance is not specified on the drawing, as it is already specified on the thread sizes standard. Or for example, when indicating a 16-gauge steel sheet, which follows a different standard. Now we'll see the importance of the location of dimensions in our drawing. Please calculate which is the maximum value that can be at the distance x. Pause the video and resume when you have the answer. Ready? A simple way to do this is to separate the dimension from its tolerance. Then, sum the dimensions and tolerance separately. At the end, add both amounts. And in this case, the result is 27.6. Now let's calculate the maximum value that the distance x can be. Note that the tolerances for all the dimensions haven't changed. They still 0.2. But now the result is 27.4. For the last time, calculate the distance x. Now we can see that the dimension is directly indicated. So in this case, the maximum distance of x is 27.2. With these three examples, we have seen how the total length varies by changing the locations of dimensions, although these have the same tolerance of 0.2 in the three examples. The dimensions must be chosen and located to meet the function and assembly with adjacent components, and should not be subject to more than one interpretation. In the first case, the individual dimension is the most important, and in the third case, is more important each dimension with respect to the base. We have seen how by changing the location of the dimensions, change the tolerance stack, also known as stack-ups. Now let's see a couple of things that differentiate a drawing dimension on inches from millimeters. When a drawing is expressed in millimeters, if the distance is less than 1 millimeter, a 0 is placed before the decimal point. And when it is an integer, neither 0 nor the decimal point is displayed. Here we can see the two examples. At the top, dimensions are specified in inches, and at the bottom in millimeters. In this case, we can notice because dimensions smaller than 1 have a 0 before the decimal point. In this case, they are millimeters. Please identify each group of dimensions, either if they're expressed in millimeters or inches. Find the zeros before the decimal point or integers dimensions without decimal point. Pause the video and resume when you have the answer. Ready? Here are the results. The group of the left is noted in millimeters. Notice that 12 doesn't have a 0 after the decimal place, and the 0.9 shows the 0 point before the decimal place. While on the right side we have inches. We can see all these dimensions that are less than 1 and don't have a 0 before the decimal point. Conclusion: ASME Y14.5 standard contains fundamental rules to standardize engineering drawings. It is not limited only to geometric controls.